All right, if we had a first law of thermodynamics, you knew a second law was coming, didn't you? And here it is, the second law of thermodynamics. Lecture covered the first law, we'll move on to the second law. The second law is actually uh, pretty counterintuitive, um, and unlike the first law, which I think makes sense. First law basically says energy in minus energy out is your change in energy. We can understand that. Second law of thermodynamics is a little bit more uh, brain boggling. But in that way, it's also more interesting. So let's start with our heat engine. So we have our heat engine here, and if you remember, if we put in heat, right, our piston's going to expand. It's going to do work on the environment, right? It's going to turn our car engine or whatever. And then we're going to eject some heat and the piston's going to go back to its normal spot. When we write this in a thermodynamic graphic, it looks like this. Okay, so we have a temperature reservoir at TH. Um, QH goes in, that's this uh, uh, putting in thermal energy. Some of that thermal energy gets turned into work, and some of it we need to get rid of by sending it into what's called a cold reservoir, or in the case of our engine here, just the environment, right? QC is waste energy. It's not being used to actually get some work done, right? So we have all this energy we're adding to the system. We want to use all of that to create work. Um, but inevitably we have waste heat. And that is what the second law tells us, is we can't get around that. The second law has many different statements, but one of them is it's impossible in any system for heat energy to completely convert to work in a cyclical process which returns to its initial state. So here we have a cyclical process, right, that we're going to have the piston here, it's going to go in, and it's going to come back out to the same point, and then we're going to repeat our process. So that makes it a cyclical process. Basically, it's saying we can't do that without a Q out. It's just not going to work. And if you think about that physically, what that means is we can't get that piston back here unless we get rid of some of that gas, um, unless we get rid of some of that heat to cool our system back down. So uh, that's the second law, that basically you can't have a perfectly efficient engine. And this is the fascinating part, is it's not bad design, right? It's not friction, drag, bad insulation. It's just physically impossible. And that is a little hard to get your head around. So let's look at that in terms of efficiency. We write efficiency with this little Greek eta. Looks like a capital script N. And we can write this as, okay, our efficiency is the amount of work that we get compared to the amount of heat that we put in, right? So we're putting in all of this heat energy. We want to turn all of that into work, right? If we were able to do that, then our efficiency would be 1, right? Our work out would be the same as our heat in. That doesn't work very well. The amount of work that we get is, because QC must be non-zero, the amount of work that we get is what we put in minus what we have to waste, right? So that's what this equation means. Our work out is our energy in minus our wasted energy. And then we can do a little bit of algebra and turn that into this statement right here, okay, which is a sort of standard statement of efficiency. Ideally, we want that to be 1, but the second law tells us that because this can't be 0, this is always going to be less than 1. Okay, that's the heart of the second law. You can't have a perfect engine that's going to turn your thermal energy into work. Okay, but what if we did have a perfect engine? What kind of efficiency could we achieve there? Um, well, this idea is called a Carnot engine, an ideal heat engine, that we basically don't have any non-conservative forces. We don't have any friction. We don't lose any energy to our environment. And it looks like its PV diagram looks like this PV diagram right here. Before we address that, though, we need a couple of terms. One of those is adiabatic. Adiabatic means perfectly insulated. It means that no heat is lost to your environment. And then we use the term isothermal, and that means the temperature is the same. So that iso means something stays the same. Last time we talked about isobaric. Isobaric means the pressure stays the same in a process. Here we're talking about isothermal, so the temperature is staying the same. So what does this cycle say? Well, here at A, we're basically at the beginning of our piston cycle. You put in a bunch of heat here, right? And um, the piston expands isothermally. That means all of the energy going in here is going into expansion, not into changing our temperature. Okay, so that's ideal. And then here it continues to do work, right? But we're no longer adding heat. So the piston is doing work, and that work is making its temperature go down, right? Because it's doing work on the system, so it's losing energy, and it's losing some of that lost energy turns into a lower temperature, but it's not actually losing any to the environment. There's no exchange of heat with the environment. Again, this is a sort of perfect, what's called a reversible process. Theoretically, you could move between B and C without losing any energy. And then on the way back in, we need to reverse that expansion process, right? And in order to do that, to make the gases allow for this reverse expansion, we need to get rid of some of the heat, right? The ideal gas law tells us if we lower our temperature, we're going to get a smaller volume, right? And so we lower our temperature, again isothermally, and again we finish that expansion adiabatically, that is without losing any energy to the system. So this is a theoretical ideal PV diagram for an engine. So what kind of efficiency does it have? Well, because of these isothermal expansions, we can actually replace our QH and QC with TH and TC. That is the temperature at which the heat is being added and the temperature at which it's being removed. And you get this restatement of efficiency for a Carnot engine. Now what's interesting about this is, well, these temperatures are in Kelvin, right? So are we going to be able to have 0 Kelvin here so that we can get a perfect efficiency? Not even close, right? Basically, you have to have a reservoir that has no energy in it for this to be perfectly efficient. We might, if we're lucky, have this at 300 Celsius, and that means that this number is going to be substantial. Okay, this fraction here. And in fact, when in real-world applications, even a Carnot engine isn't going to have an efficiency much better than about 70%. So that's disappointing for those of you hoping to build a continual motion machine.